Welcome to the Explainer. For generations, the idea of firing concentrated beams of pure energy to defeat an enemy, well, that's been firmly locked in the realm of science fiction. We all know the classic image, right? The silver screen ray gun blasting neon bolts across the stars. But what was once just a flashy movie prop is quietly moving out of the theater and onto the actual battlefield. Today, we're looking at the very real directed energy weapons that are being deployed on ships and trucks right now. It's a question that sounds almost absurd until you look at where modern defense budgets are actually going. Military forces all over the world are currently investing heavily in systems that neutralize targets using nothing but light, sound, and microwaves. We are witnessing a fundamental, ground-up shift in how warfare operates. We're moving away from traditional solid projectiles and explosives and moving toward the manipulation of the electromagnetic spectrum. So, here's our roadmap for this explainer. We're going to look at From Fiction to Reality, the history of energy weapons, how a directed energy works, modern battlefield applications, limitations and current challenges, and finally, the future of warfare. Okay, let's dive into Section 1, From Fiction to Reality. Picture this. It's the 1930s, and rumors start swirling around Europe about a mysterious engine-stopping ray. The story went that tourists driving near a German television transmitter in Feldberg would mysteriously have their car engines just die. A sentry would tell them to wait, and then 20 minutes later, their cars would magically start again. Sounds like a sci-fi weapon, right? Well, in reality, sentries were literally just stopping traffic so the electrical noise from the car engines wouldn't interfere with field strength measurements for the TV transmitter. It was totally mundane. But British intelligence, they seized on this myth. They actively relaunched the rumor as a highly secret British engine-stopping ray. Why? To deliberately spoof the Germans into researching this fictional weapon. It was a brilliant move, tying up and wasting precious German scientific resources right before World War II. Moving right along to Section 2, the history of energy weapons. The dream of directed energy is actually ancient. Legend has it that the Greek mathematician Archimedes used a massive array of mirrors to focus sunlight and burn Roman ships attacking Syracuse. Now, modern historians and experiments suggest this was likely more myth than practical reality, but the concept itself never died. Jump to the 1940s, and Axis engineers actually developed experimental sonic cannons. They pulsed methane gas at roughly 44 hertz into parabolic dishes. This created sound waves specifically designed to cause extreme vertigo and nausea by vibrating the fluid in the inner ear. By the 1980s, the ambition moved to space. Under Ronald Reagan's Strategic Defense Initiative, famously nicknamed Star Wars, the United States tested neutral particle beam accelerators. They even successfully operated one in space in 1989 to see if it could shoot down intercontinental ballistic missiles. Fast forward to the 2020s, and we've moved past experimental particle beams into the actual real-world deployment of 300 kilowatt class solid-state lasers. Which brings us to Section 3, How Directed Energy Works. By definition, a directed energy weapon, or DEW, damages its target without firing a solid projectile. Instead, it relies entirely on highly focused energy, and the absolute game changer here is that this energy travels at the speed of light. Because it doesn't have mass in the traditional sense, it's virtually immune to gravity, windage, and the Coriolis force that causes standard bullets and artillery shells to drift off target. For all practical purposes, you get an almost perfectly flat trajectory. Literally, if you can see the target, you can hit it instantly. And this perfectly illustrates the difference between the two main types of electromagnetic weapons we're seeing today. Think of high-energy lasers like an incredibly long, invisible blowtorch. They deliver pinpoint accuracy, focusing a continuous or pulsed beam of infrared light to physically melt through a drone's plastic wings or a mortar's metal casing. High-power microwaves, on the other hand, are more like an invisible floodlight. They operate at longer wavelengths and emit massive bursts of power. We're talking sometimes over 100 megawatts. Instead of melting a target, this super wide beam penetrates the shielding and violently disrupts or straight up destroys internal electronic circuits. It's basically the difference between using a sniper rifle to melt a single drone and using a shotgun blast of energy to drop an entire swarm of drones out of the sky all at once. Let's look at how this is being used today in Section 4, Modern Battlefield Applications. The sheer variety of deployed tech is absolutely fascinating. We aren't just talking about lab experiments anymore. In the naval sector, defense contractors like Lockheed Martin have developed systems like Helios, which are actively integrating high-energy lasers right onto warships to defeat aerial and waterborne threats. Over in the UK, they're developing the Dragonfire, which is a 50-kilowatt class line-of-sight laser expected to equip ships and ground vehicles by 2027. But, it's not all massive vehicle-mounted systems. On the battlefields of Ukraine, both Ukrainian and Russian forces are heavily utilizing shoulder-fired electromagnetic anti-drone rifles, like the Ukrainian KVS G6 or the Russian Stupor. They look like these thick, futuristic rifles, but instead of firing bullets, they emit directional electromagnetic pulses. This severs the connection between a drone and its operator, causing it to just drop right out of the sky. Now here is the single most compelling reason why militaries are rushing to adopt this technology: 13 cents. That is the reported cost per shot of the UK's radio frequency directed energy weapon. Think about the math for a second. When an enemy launches a swarm of cheap $1,000 drones, defending against them with traditional multi-million-dollar interceptor missiles is an unsustainable economic losing game. But if your ammunition is literally just electricity and each shot costs only pennies, you fundamentally change the economic math of modern air defense. You effectively have an infinite magazine, constrained only by how much fuel is in your generator. It's also really important to note that not all directed energy is intended to be lethal. Sound is a form of directed energy too. Long-range acoustic devices, or LRADs, focus sound into a really tight directional beam. Back in 2005, when Somali pirates attacked the commercial cruise liner Seabourn Spirit, the crew successfully repelled them by firing an LRAD. The device projected an intolerable, ear-splitting barrage of warning tones over a huge distance. It completely forced the pirates to retreat without the crew firing a single lethal shot. But it's not all perfect. Let's get into Section 5, Limitations and Current Challenges. So, here's the catch. Manipulating the electromagnetic spectrum comes with some severe environmental penalties. While lasers travel straight and fast, they're incredibly easily defeated by heavy rain, fog, or dust, which scatter and absorb the light. Plus, they require massive, heavy power supplies and super complex thermal management systems just to keep from melting themselves. They're also strictly limited to line of sight. You can't fire a laser over a hill to hit a hidden target like you could with a traditional artillery shell. Furthermore, there's a really tricky physics problem known as thermal blooming. Basically, when a high-powered laser heats the air it passes through, that hot air actually acts like a lens, defocusing and diluting the beam before it even reaches the target. And as for microwave weapons, because the beam is so wide, you run a very real risk of accidentally frying your own friendly electronic assets in the crossfire. Finally, let's wrap up with Section 6, the future of warfare. The Center for Arms Control and Non-Proliferation highlights a critical reality that really grounds all this technological excitement in real-world policy. They basically hit the nail on the head, pointing out two massive hurdles. First, our industrial supply chains simply aren't ready to mass-produce these highly complex, specialized optics and power systems at a global scale. But more importantly, the international community completely lacks the ethical and legal frameworks to govern them. The lines between non-lethal disruption and lethal force are seriously blurring. Weapons that target electronics or cause temporary biological effects operate in this massive gray area of international law that hasn't been fully defined yet. And that leaves us with a pretty profound question to consider. As the mechanics of warfare literally accelerate to the speed of light, are our international laws, our ethical boundaries, and our industrial capacities actually equipped to keep pace? The ray gun has officially left the realm of science fiction, and it's now up to us to figure out how to live with it in reality. Thank you for joining me for this explainer. Keep questioning the world around you and stay curious about how technology continues to shape our future.